Hello and welcome back to another LeetCode problem. So today we're going to be doing problem number 2542, maximum subsequence score. And you're given two arrays, nums1, nums2 of length n and a positive integer k. You must choose a subsequence of indices from nums1 of length k. And the way this works is you choose some subsequence. It doesn't have to be contiguous. So we can choose any one of these numbers. So let's say we choose, our k is 3, so let's say we choose like 1, 3, and 2. And then from nums1, they have to match the indices, so we would choose these three numbers. And the way it works is we take the sum from nums1, which would be 6, and we take the minimum out of everything we've chosen in nums2, and that's going to be our output. So the minimum here would be 2, so it'd be 6 times 2, and then we're going to get 12 here. So this is kind of a tricky problem because there are a lot of things we need to do. We need to try to maximize the sum while minimizing the min. Also, this subsequence, it says you have a subsequence that is a set that can be derived from the set this by deleting some or no elements. So this isn't a continuous sequence, so we can't do some kind of like a two-pointer technique or something to just go through this and maximize the sum. And at first when you look at this, you might think it's a dynamic programming problem as well, because there are a lot of dynamic programming problems where you have some subsequence with deleted elements. But the problem is you're trying to maximize the sum and you're trying to minimize the min, and it's really hard to get a recurrence relation for that. And also, if you try to do some brute force or memoization, it's also quite difficult to do. Like what's the base case and what's the recurrence relation? Like it's very hard to do that. So let's try to actually, for one thing, we can notice that because, so normally when you have a subsequence that you can delete some elements from, it has to be in order. But they're asking us to get the sum from the left and the minimum from the right. So if we have something like this, like let's say we pick these three numbers, and then from the right that would be 2, 1, 3. So the result for this would be 7 times 1, so it'd be 7. Does the order of this really matter? Like what if we just swap these around and we do maintain this relationship, but what if we do something like this? So it'd be 3, 1, 1, 2, 3, 3, let's say. Well, that's still the same thing, right? So the sum of this is 7 and this is still 1. So it's still the same answer. So that tells us that we can actually probably sort this because the order of the elements doesn't actually matter. Like a sum in any order is the same sum, and the minimum in any order is the same minimum as long as we're maintaining this. So instead what we can do is we do want to maintain this one-to-one, but let's say we sort it. And how do we want to sort it? Well, the order doesn't matter, but let's try to, well, it does matter is the minimum, right? Because if we sort by this second column, then we would know exactly where we are for the minimum. So for example, let's sort this second column, and we're going to sort it from highest to lowest. So it's going to be 4, 3, 2, 1, right? And then this is going to be 2, 3. So 3, 3, and then there's a 3, 1 here, I believe. And then it's like this. So this is N1, N2. Okay? And our subsequence is 3. So if we wanted to get to 12, we could still get to 12, right? So just in this case, it would be this. So this would be 7, and then this would be times 2. So that would still give us the same output as before. But, so we have subsequences of length k, but once we do have the sorted thing, what do we do from there? Well, we could just try to get a minimum subsequence and then see what happens. So let's just get the first available minimum subsequence starting from the left, which would be this, right? So we need 3 elements. So this is 12 because this is 7 and then we take the minimum here. Well, let's say we want to use this 1 now maybe. What would we do? Like we can take a minimum subsequence with every single minimum. So like if this was longer, we could have a 2 minimum, a 1 minimum, we can keep going. And we can realize that when we have some subsequence, the only numbers that really matter are the sum and the minimum number. Do these numbers really matter? Does this 4 and 3 really matter? As long as they're bigger than the 2? What if they were 10 and 9? That doesn't matter. So the only number that really matters in our subsequence is the actual minimum and the sum. So let's try to maybe have a subsequence with a 1 that is the lowest, right? So let's say we move on to this 1 and we try to get a subsequence that has the smallest number 1. Well, how would we change our original subsequence to do that? Well, what we can do is we can take this 1 and we have to get rid of something, right? So now our lowest is 1. So remember, anything above it doesn't really matter. Like, it doesn't matter which one of these we keep because the smallest is going to be 1. So then what would we remove from the top if that's the case? If it doesn't matter what we remove from the bottom, what would we remove from the top? Well, we're probably going to want to remove this 1, right? Because that is what we're going to want to remove is the smallest number that affects our sum. And so our recurrence relation here is we're going to move down. We're going to try all subsequences with a different minimum. And then we are going to simply remove the number from the sum that is the smallest. And so if we're trying to maintain a running total of the sum, and we have to keep trying to remove the smallest number, what data structure lets us remove the smallest number easily? Well, it's going to be a heap, right? And so we're going to have these numbers in the sum of the heap, and we're going to move down. We're going to keep changing our minimum. Now, the other thing that's kind of cool is you might think we do have to keep track of the current minimum, but let's do some other examples. So let's say this is like this, but now this is a 0. And so we have this starting k, right? This is going to be our initial k, and then we move down to this 1, and we say, okay, our smallest 1 is a 1, or our smallest number is a 1, so what do we remove? Well, we're actually going to want to remove the number that's associated with a 1. So does that mean we have to update our minimum to 2? Well, no, because basically, in this case, we're always going to check what's our result compared to a previous result, and we're going to take a max. And so if this is the case, if the number we added is the one that's going to be removed, it doesn't matter because the minimum here this will basically be the same thing as this thing on the left, right? So this thing on the left, our total is 12. But then when we remove this 0 and we do say our minimum is 1, this is still going to be 7 or 6, sorry, and it's going to be times 1, which will be 6. And 6 is smaller than 12, so if we remove the number that we just added, it doesn't really matter for the sum because our result is always going to be smaller than a previous result, so it'll never get updated. So that's not something we have to worry about. So we don't have to keep a running total of which like we don't have to add the minimum into the heap somehow, because even if we removed something that is with this value, if our previous heap is the same, then our total will just never get updated. And we are guaranteed to have a starting total because when our heap is first filled, we're going to start our output at like, so I think these numbers have to be positive, so we can just start our output at 0, and so when our heap is filled, we're going to have a guaranteed output. So hopefully that makes sense. So we're going to be traversing, we're going to sort these numbers, and we're going to maintain this relationship, right? We're going to maintain this relationship. We're going to keep adding these numbers into the heap, and we're going to keep a running total of the sum, and we're just going to see what do we throw away and what's the sum and what's our minimum value, and we're just going to try all combinations with every single minimum value. So we're just going to go down the pairs. Okay, so hopefully that makes sense, and let's code it up and I can explain it a little bit more in the code. So first what we're going to want to do is, like I said, we're going to want to maintain this index relationship. And yeah, these numbers are positive. So we are going to want to maintain this index relationship. So we could do that one of two ways. We could just have an index, and then we can just add these numbers. Like we can just say for I in whatever, take both of them. But also Python has a zip function, so we can use that instead. So let's just make a new data structure here, I think. Because we're going to need to have a heap anyway, so our time complexity isn't going to get affected too much. Okay, and so let's do that. And also we are going to need to keep these separately. So let's just say this is going to be, what do you call it, subsequences maybe, equals, and so in Python you can do something like this. So you can do A, B, for A, B in zip, and then you can zip these up. So a zip actually doesn't return a list in Python. It's another data structure, but you can still iterate through it. So I believe that should work. So let's just test it. Okay. Okay, and then we can try to print it just to see. Yeah, so we have a list comprehension that we made a list out of the zip because yeah, if you try to just zip them up, it's not going to give you a list. Okay, and then we need to return. Just do this and see if what we had is correct. Right, so it zipped them up together. Now the other thing we need to do is remember we need to sort the subsequence, and we need to sort the subsequence by the second element, and we need to sort it in reverse. So the way to do this, I think, is subsequences dot sort, but then you have to pass in a custom sort parameter. If you don't pass in a custom sort parameter, it's gonna sort by the first element, and it's also not gonna do it in reverse. So you need to do something like, I think it's key, don't remember 100%, but I think this is lambda, and then this is just x1, meaning the second element. And then I think you also need to do reverse equals true, I believe. So let's see. Okay, so I think that's fine. And then we can print it again just to double check here. And I'll go over how that works. Okay, so so it's sorted, so you can see that our relationship is still maintained, right? So 2 to 4, 3 to 3, 1 to 2, 3 to 1, but it's sorting by the second element. So what this does is this sort does have multiple parameters, and so if you want to sort by the second element, or if you want to sort by some kind of equation, you have this key, and then you have a lambda equation, and lambda just means use it right now. We're not going to use it somewhere else, so you can put in this equation. So if you wanted to do something else, you can even do something like, let's say you wanted to like square the second element or whatever, you can just do like this, I believe, as well. So you can put in whatever equation you want. But this just simply takes the second element in each one and then sorts them. And then reverse equals true means we want the reverse of the list. So if we get rid of this, this would be ascending order. Okay. So now we did that. Now what we need to do is, remember in our picture, right? So we need to go through this whole sorted thing, and we need to keep adding these numbers to the heap, and then let's say we have a k, so we can keep adding to the heap, and once the heap overflows, so once we have too many items, then we need to pop the smallest sum out of the k. And then, like I said before, it doesn't matter if we pop what we just pushed, and even though this is technically 2, because this will never get updated, so it's fine. Okay, so let's make a heap. And then so we need a running total for the sums because our output variable is going to be the running total of the sum. I believe it's times the smallest element that we're currently on. So let's do that. And then we also need a res. So our res is going to start at 0 because we're going to want to maximize it. So we start at 0. And our total is going to start at 0. Okay, and I think that's all we need for that. So then we need to iterate through this subsequences. So we can just say for A, B in subsequences. We need to add the A, right, into the heap. So the A is going to be the element that's in nums1. So let's do that. It's going to be a heap push. So by the way, also when you're using LeetCode, all these heap functions use a class called heapq. I think it's either heapq or heapn. I believe it's heapq. But because you're doing it in LeetCode, all these imports are already in there, so you never have to do like math dot or heapq dot or collections dot or whatever. But in a real interview, if you did have to do imports, you might want to make sure you know those as well. Okay. Yeah, I think it might be heapn or heapq. I don't remember 100% which one, but okay. So we're gonna heap push, and then we're gonna heap push A. Or no, actually, so for a heap push, first you say where you're pushing to. So it's gonna be heap, then it's gonna be A. Sorry, it's a little early in the day, making too many mistakes. But so heap push, heap A. Now what we need to do is we need to check, is our heap full, or is our heap even normal sized, right? So first we're gonna check if it overflowed, and then we're gonna check. So because like let's say here our heap size is 4, what we're gonna want to do first is make it one smaller if we need to, and then we're gonna check for the result. And that'll work also when our heap isn't full. So if we only have 2 elements, we're gonna check did it overfill. Well, no. So we're gonna want to do that before we calculate the result. So if length heap is greater than k, right? That means it overflew. Then we're just going to need to pop it. And to do that, we need to do a heap pop. So I think it's heap pop. Or it might be heap pop, not 100%. Okay, so I think, yeah, so heap pop, and then you just pass in where you're popping from. And so because it's a min heap, in Python, every heap is a min heap, and we're going to pop the minimum number out. If you wanted to do a max heap in Python, what you would do is you would take every number. So let's say you had these numbers like this, and you wanted a max heap instead. Well, what you could do is pretty simple. You would just pass them in as negatives, and then the max heap would still give you the minimum value, right? But the minimum value now would be this, and then you can just multiply by -1, and that would be max heap. So that's how you do that. Okay, so we heap pop. Now we actually do need to keep track of this value. So we need to actually do something like this, right? Because we got rid of some number, we need to subtract that from the total. Okay, now what we need to do is we need to check, okay, if our heap is equal to size k, which it will be if we're either on this part, right, when we actually have 3 elements and we want 3, or if we have put in our 4th element and we popped it. But if we only put in 1 or 2 elements, then we're not going to want to check for the result. So that's what we need to do. So if length heap equals, this is going to be k. Now we need to check for a result. So res equals max res, and remember it's going to be the total times this b is going to be the current minimum that we're on. So it's going to be times b. And then we just return res here. And so hopefully that makes sense why we don't need to actually save this b value, because even if we do pop what we currently put in, it's just not going to change the total, so it doesn't matter. Okay, so let's try that and see if we screw anything up here. 0, expect 12. Interesting. Okay, probably did something ridiculously silly as always. So nums 1, nums 2, expected 12. So we heap push, if length heap, oh right, yeah, of course. So we need to increment the total, and then we never did that. Okay, let's see. Okay. Alright. I might be doing some more of these daily codes. This was definitely, I would say if it's a medium problem, but it's definitely super hard to figure out because it's not super intuitive, and I think a lot of people will try to do this in dynamic programming and just realize it's very hard to get a recurrence relation. Okay, so now let's try to figure out the complexity here. So time. Okay, well, what are we doing? So here we are just zipping, which is just going to be the length of the list. This sort is going to be n log n. So already our worst case scenario is n log n. Let's see what we're doing for this heap now. So for every single item, we're doing a heap push. And a heap push, so heap pushes and heap pops take log n. And so we're doing this for every single item. And so it's just going to be like this. It's going to be a heap push and a heap pop, so it'll be 2 times n log n, which would just cancel out. And so I believe that the time of this is going to be n log n, time of this is n log n, and so our total time complexity is n log n. Okay, what about space? Well, for space, what are we storing? So we did make the subsequences array, so this is going to be O of n at least. And then we also made a heap, and a heap, what's this k value equal to? So this k value can be n, and so our heap can store maximum, same thing, of n values as well, because if k is equal to n, then we would store the entire array. So that would be n as well. Okay, yeah, so I think this is n, and this is max worst case n, so this would just be n. And that's why making this array is not so bad, because this heap will be the same time complexity. What you could have alternatively done probably is instead of making this new array, you could have just you could have just modified one of these, and that would technically save you some space, but that's also not great practice. So, okay, so I think that's it for this problem, and if you like these kind of problems, like and subscribe, and I'm going to continue to make a lot more of these in the future. So thanks for watching.